Good morning. My name is Bhavesh Kumar, and I'll be speaking about reimagining simulation to drive post-COVID cost reduction initiatives in the automotive industry. We all know that simulation is not a new technology. It has been around for decades, and it has evolved so much that today we can invoke Arthur C. Clarke's famous third law. Any sufficiently advanced technology is indistinguishable from magic. On the left is a paper that was published by Porsche way back in 1988 about their experience of working on nonlinear structural simulations for 7 years on a Cray supercomputer. Porsche called this a progressive trend in the automotive industry. On the right, you're looking at a realistic rendering of simulation results from offset and side crash analysis. The level of details that can be captured today are nothing short of phenomenal. And this means that simulation results are more closer to realistic scenarios than ever before. At the same time, texts and numbers are now replaced with such lifelike visualizations, which are becoming more common. When I started running simulations, I thought those colorful contours were beautiful. And now we can even look at these results in VR and AR. We come across trends and predictions all the time, but we hardly look back at them. In 2008-9, Mark Halpern from Gartner presented on product performance simulation in the year 2020 at a regional NAFEMS event. Halpern categorized the simulation technologies based on two axes: the impact on design success and the maturity level of simulation technologies at that time. Interestingly, the two technologies that you see, multiphysics and system simulation, today are becoming more and more common, more and more critical, while the other two technologies, stochastic simulation and complexity analysis, are today subsumed into the broad field of data science, the use of artificial intelligence and machine learning on simulation and test data. In 2020, unfortunately, what we are facing is a global COVID scenario, a disruption nobody would have thought of in 2009 or even in 2019. So the question is, can simulation be reimagined to tackle these new challenges? Does simulation have the sufficient punch to deliver business goals as against just engineering goals? The answer is yes, but before that, let us understand what we know about the value that simulation provides today. From using simulation to understand failure, companies have largely transformed the use of simulation to predict product performance, optimize product designs such as for lower costs or better performance, durability, and generally reduce the number of tests and prototypes, thereby reducing the overall cost. If we have to reimagine simulation, we have to expect more from simulation, managing complexities, sustaining confidence of consumers, and mitigating risks. This is what I mean by simulation having sufficient punch to deliver business goals. Any technology, as we know, goes through an S-curve of adoption, which means that when a technology matures, smaller and smaller improvements come at greater and greater cost until it is replaced by a new technology. We have seen this in the case of smartphones. The disappearance, the replacement, and the amalgamation of technologies over decades that we hold in our hands now as a smartphone. Sometimes in the future, I am sure we'll have other form factors, but the lockdown has made it clear that we love our smartphones the way they are right now. Simulation ultimately is a technology too. You may ask, where is simulation on the S-curve? Now with simulation, we also have different technologies representing different physics: structural, fluid, thermal, electromagnetic, and so on. And they are all at different levels of adoption and maturity. However, what is clear is that all these technologies are largely driven by experts. And this is not unreasonable given the extent of understanding that is generally required. However, for any technology to make an impact, it is also necessary that its benefits spread across an organization. And this is exactly how left shifting of simulation started. The use of simulation more and more upfront to figure out what could go wrong and redesign appropriately, rather than finding out why the vehicle broke down on the road. An optimization study can provide the best possible design with minimum weight and maximum performance. But this is of little use unless it can be manufactured. A detailed vehicle dynamics analysis can provide the best possible ride and handling, but this is of little use unless the design is robust and reliable. So we start seeing dependencies emerge all over the place. Simulations, tests, designs, manufacturing, all of this managed by different applications, different departments, and different stakeholders. And this is why a systems engineering approach makes sense in today's complex world. If simulation has to be reimagined to provide more punch, then model-based systems engineering is the way to go. In fact, model-based systems engineering or MBSE also becomes necessary for digital or virtual twin, what we in Dassault System call as 3D experience twins. The reason is that simulation pervades throughout the complete project, right from requirements to functional and logical representations, to physical models and behavior, to manufacturing, and even to in-service scenarios. With this, I would like to cover two broad areas where simulation will play a critical role and is already playing, not only in terms of performance validation, but also in terms of reduced costs. The first is on reduced emissions to demonstrate the increased adoption and trust in multiphysics simulations. We have had BS6, and while we have worked with many customers on pushing the boundaries of simulation for BS6, I would like to use WLTP, which replaces NEDC in Europe. With WLTP, the challenges are twofold. The first is higher emissions reported with WLTP cycles, which are more realistic. The second is massive increase in testing because every vehicle variant has to be certified. After WLTP was introduced in 2018 in Europe, there has been a 24% decrease in vehicle registrations. WLTP, therefore, seems to be just the right challenge for simulation to be reimagined, and this is precisely what is happening. If simulation has to help in certification or digital certification of vehicles, there are many scenarios that need to be simulated with accurate and fast multiphysics solutions. Powertrain, aerodynamics, rolling resistance, and even exploring solutions through lightweighting and electrification. I will cover just a couple of these processes. While we do not have WLTP in India, these simulation processes are currently deployed by customers in India to potentially reduce emissions. The first I would like to cover is vehicle aerodynamics, and more specifically, aerodynamics under real-world conditions. Traditional aerodynamics is based on testing under wind tunnels, or sometimes simulation of what happens inside a wind tunnel. Now, the fluid simulations, as we know, can be very accurate, such as the one that you see here from PowerFlow, and can not only predict how the air flows over different regions, but also help recommend changes that can reduce the aerodynamic drag and provide a better aerodynamic performance. The video that you see here first takes us through the aerodynamics in the wind tunnel, considering how design changes can be suggested to reduce the aerodynamic drag. So far, so good. We have seen the improvement in the wind tunnel, and the question that arises right now is how will this translate to real-life driving conditions? First of all, real-life driving conditions are transient, not steady state, and that has to be considered for any simulation. Secondly, there is changing wind direction as well as turbulence that needs to be captured well. And thirdly, the effects of rotating tires as well as any other active devices should also be considered. So what simulation allows here is not just the ability to make decisions based on real-world performance, but also make this repeatable. The best practices for vehicle aerodynamics can be applied to any variant quickly, and this leads to much faster turnaround times through virtual validation. The second simulation process I want to talk about is powertrain structural performance. And in fact, this is one of the oldest simulation workflows in the automotive industry. However, with increased demands on emissions and fuel efficiency, the usage of advanced simulation technology for powertrain has only increased in the last few years. While some powertrain workflows, such as durability, have been standardized over the years, some, such as exploring lightweighting alternatives, provide more interesting challenges. One is the use of alternative materials. This introduces the classic cost performance question. Alternative materials are not just applicable to powertrain, but to pretty much all aspects of automotive design. And there is both the cost of material as well as the incremental cost of manufacturing, if any, that needs to be considered. Similarly, if we consider the performance part of it, it is complex too because there are multiple disciplines. And this is the reason why multidisciplinary optimization, or MDO, has been around for so many years and is in fact seeing a revival lately. However, silos between different disciplines also lead to MDO not being utilized to the fullest extent. And this is where collaborative platforms that rely on data-driven digital continuity really help. The idea is to start from a single source that can be used and reused across multiple disciplines and multiple departments to provide the best possible and the optimal design. So I covered simulation for reducing emissions to demonstrate multiphysics. And the second broad area I want to cover is electric drive engineering. And this is to demonstrate model-based systems engineering in action. Consider an electric drive. On the modeling side are a set of requirements, service conditions, use cases, context, stakeholders, and so on. And on the simulation side, there is a whole gamut of workflows to be covered, from conceptual design to detailed design. So instead of explaining all the workflows, let me just run a short video on how multiphysics and system simulation work for electric drive. We start with a broad set of requirements: the driving range, efficiency, and performance. The next step is to analyze and explore the system architecture through initial system modeling and simulation. This could involve a top-level trade-off analysis, for example, between a single drive and a dual drive, or just explore different configurations for a single drive system to come up with the best possible configuration. In this case, we will go with a single drive system as it suits all our requirements that we had specified upfront. After that would come the motor optimization based on the parametric baseline design. The objectives could be multiple, such as minimizing mass, maximizing torque, minimizing temperature efficiency, or just maximizing efficiency. The objectives could be multiple, as we have seen, and the parametric design makes it easier to quickly run a series of design exploration runs and arrive at an optimal design. Once an optimized motor design is found, further analysis could be done on a full 3D model. Once again, a fully parameterized model, which makes it easier for any what-if analysis or thermal management and structural durability to be performed. We could even look at reducing the weight of some of these components, such as support brackets, using techniques such as topology optimization, or improving the durability or life through shape optimization. So here we are seeing topology optimization being used to reduce the weight by about 18% for one of the brackets. Now that we have a good initial design, we can perform standard analysis such as structural durability to ensure that stresses are within the limits that we have defined, or a thermal analysis to ensure that there is sufficient cooling. And at any given point, we can explore design alternatives rapidly to get the better performance. So here we are looking at thermal management, optimized coolant passages that reduce the temperature, as well as looking at improved end coil cooling by changing the number of injectors. We could even look at churning losses, for example, due to gear lubrication. Ultimately, all this information can be analyzed by the system architect to ensure that the set of initial requirements are thoroughly met. And what is more, we could even look at the traceability of each and every response and change so that we are able to link every response to the functional requirements as well as to the broad requirements that we had set at the start of our project. And this leads to an upstream and downstream visibility of parameters. So there is a framework of requirement, functional, logical, and physical simulation, which is augmented by orchestration and governance. And this establishes a digital continuity throughout, linking modeling and simulation together. So this is fundamentally what model-based systems engineering is about. In the new paradigm, virtual validation is predictive, it is automated, and it is intertwined with generative design and physical testing. Virtual validation is at the center of decision-making process, whether it is in reducing costs or improving performance. And if it is not, then it definitely should be. I also want to touch upon another aspect here. Going digital is at the heart of many organizations today as they move from new product development to what we call the new experience development. Simulation basically is digital. It is inherently digital. Thus that sometimes there is just too much of simulation that it becomes quite complex. And simulation is either left out of the digitization strategy or is pushed to a subsequent phase of implementation. And this is precisely why model-based systems engineering is needed. Finally, if we consider from a cost perspective, based on the inputs that we have from European OEMs with whom we have worked over the years on areas such as WLTP, the cost savings go from €1,000 per hour in wind tunnels to €100,000 for shorter test trips. Of course, this assumes that we can trust the simulation results. One of the reasons why I showed the two examples, vehicle aerodynamics and powertrain durability, is to simply emphasize this. Simulation results can be trusted, and what is more, simulation results can be closer to reality. Reimagining simulation is not just about application of better technology, but also about maximizing its impact to the business. In the post-COVID scenario, I only see the role of simulation increasing exponentially. Thank you very much. So we have just time for a couple of questions. I already see the first one. It is, how do you see the adoption of artificial intelligence and machine learning in simulation? What I would like to say is that there are a lot of applications today that are finding use through artificial intelligence and machine learning. I would broadly put them under three categories. The first one is obviously in terms of automation. As we know, there are so many activities that we do for simulation workflows that needs automation. It's macros, custom scripts, and so on. And this is where the machine learning algorithms are playing a vital role. The second is in material calibration. Alternative materials, as I talked about, it's a big area of research. People are always exploring new materials. In fact, there are companies which design materials the way other companies design products. And once you have these new materials, from a simulation perspective, what is required is to have the correct material data, the correct material properties. And this is again where AI and ML are being used extensively. And the third area that I can talk about is just data science itself. And as we know, simulation throws out a lot of data. Not just simulation, but there is test as well. If we are able to put in all the test data that is available, is it possible to get more insights from all of this data? And this is exactly where data science is being used. And we have a second question, which is very interesting. Do you see simulation replacing tests and prototypes completely, or companies actually using simulation that effectively to eliminate tests? That's a great question. And, we've always been talking about simulation replacing tests, simulation replacing prototypes. And what I would like to say is that simulation helps in rationalizing the number of tests and prototypes that need to be done. And we have seen that the budget that any company has for testing and prototype, it really doesn't go down. It keeps increasing. But the idea is that there are certain standard tests that could be eliminated by simulation, but then new requirements come up, which means that eliminating prototypes for certain functionalities for certain disciplines. And over time, we would see that this trend would continue, and simulation would really help in rationalizing the type and the number of tests and prototypes that need to be done. Thank you.